Welcome to this workshop on meta-analysis. In this module, I'll run through a meta-analysis that looks at the impact of statins on cardiovascular events. The effect size index is the odds ratio. This video is one in a series, and I recommend this one if you plan to work with the odds ratio or the risk ratio. I'll cover the following items: how to enter data, how to run the analysis, how to estimate the mean effect size, how to understand heterogeneity in effects, how to report the results, how to create plots, and how to assess the potential impact of publication bias. I'll be using the software Comprehensive Meta-Analysis, or CMA. Our website is metaanalysis.com. There, you can download a free trial of the software and also the datasets used in this video. Overview. This analysis includes 14 studies that looked at the impact of statins on cardiovascular events. All studies were randomized controlled trials, RCTs, in which patients were randomized to either statins or to a placebo. Each study reported the number of patients who experienced a cardiovascular event. The effect size index is the odds ratio. This example is based on data from a systematic review that was published by Huffman et al. In 2013. If you're interested in the specifics of this analysis, please don't rely on this video, but consult the original paper. Let's look at the data first in Excel. The file is called statins.xls. There's a column here with the study names. There are two columns for the treated group. This one has the number of patients in the treated group who experienced a cardiovascular event, and this one has the total number of patients in the treated group. And there are two columns for the placebo group. This one has the number of patients in the placebo group who experienced a cardiovascular event, and this one has the total number of patients in the placebo group. I wanted to copy this data into CMA. I'll highlight all the relevant cells. Notice that I'm including the row with the labels. I click Ctrl-C to copy. I'll open CMA. I'll close this box. I click in this cell, and I click Ctrl-V to paste. Next, I want to take these labels and move them into the header. I click Format, Use First Row as Labels. At this point, the labels are correct, but I still need to identify the function of each column. On the menu, there's a button that I can use to insert columns, and there's a separate button that I can use to identify the function of columns. Since the columns are already in the grid, and I want to identify their functions, I'll use Identify rather than Insert. I click on the first column, and then I click Identify Column for Study Names. And the program changes the header to Study Name. I click Identify Column for Effect Size Data. The program opens this wizard. CMA will accept data in many formats, and so I need to tell the program what format I want to use. I also have the option of entering data for some studies in one format, and for other studies in a second format, and so on. At the bottom, I choose Show All 100 Formats, and I click Next. Here, I choose the first option button. This is the one that will allow me to compare two groups. I click Next. On this frame, I choose dichotomous data, number of events, because I'll be comparing the number of events in the two groups. Here, I choose unmatched groups, prospective, e.g. controlled trials. And then I choose events and sample size in each group. If I were inserting these columns, the Finish button would light up. Since the columns already exist, and I need to match each column with its function, the Next button lights up. I click Next. I need to identify the column that holds the number of events in Group A. I click here and scroll down to the column labeled Drug E. I need to identify the column that holds the sample size for Group A. I click here and scroll down to the column labeled Drug N. I need to identify the column that holds the number of events for Group B. I click here and scroll down to the column labeled Placebo E. And I need to identify the column that holds the sample size for Group B. I click here and scroll down to the column labeled Placebo N. I click Finish. The program has now relabeled these columns, calling them Group A and Group B. It also opens a wizard where I can apply my own labels. I'll call this one Statins and this one Placebo. I click OK, and the program applies those labels. These columns are now labeled Statins, Events, and Total, and these columns are now labeled Placebo, Events, and Total. By default, the program is displaying the odds ratio. To modify the display, I can right-click on the yellow columns, and I click the option to customize the display. The program opens this wizard. If I wanted to display the risk ratio, I would add check marks here. Next, I want to be sure that I understand the direction of the effect. I'll select a study where the sample size is similar in both groups. The first study works well since the sample size for the two groups is 460 and 459. There are 5 events in the statins group and 9 events in the placebo group. Since events in this analysis are bad, the statins group obviously did better. And the odds ratio is 0.549. This tells me that an odds ratio less than 1 favors the statins group. This might seem like an obvious point, but it's always worth checking. This would be a good time to save the file. I click the Save icon and I give the file a name. Now I'm ready to run the analysis. I click Run Analysis. Here, I can select an effect size index. I'll be using the odds ratio. At the bottom of this screen, I can choose either the fixed effect model or the random effects model. I choose the random effects model for 3 reasons. First, it allows me to take account of the study-to-study variance when assigning weights to each study. Second, it allows me to assess the dispersion in effect size across studies. And third, this model will allow me to generalize from the studies in the analysis to the universe of comparable studies, which is what I intend to do. Next, I'd like to set the scale for the forest plot. I right-click on the plot, I select Scale, and I set the scale to 0.01 to 100. I'd like to sort the studies by effect size so that I can get a general sense of how widely the effect size varies across studies. I right-click on the column labeled Odds Ratio, and I click Sort from Low to High. I get the sense that the effect size in most studies falls in the range of around 0.5 to 1, but there are a few studies with effect sizes outside that range. In any event, this is only intended to give me a general sense of the dispersion. We'll compute the actual dispersion momentarily. This column displays the effect size, which is the odds ratio. This column displays the lower limit of the mean effect size. This column displays the upper limit of the mean effect size. If I wanted to test the null hypothesis that the mean effect size is 1, I would use these two columns. This column gives me the z-value for that test, and this column gives me the p-value for that test. First, let's look at the mean effect size. The mean effect size is 0.710. We see that here, and we see it here. On average, in the universe of populations that are comparable to those in the analysis, the odds of an event in the statins group is 0.71 as high as in the placebo group. The confidence interval tells us how precisely we've estimated the mean effect size. The confidence interval is 0.641 to 0.786. We can see that here and here. The mean effect size in the universe of comparable populations probably falls in the range of 0.641 to 0.786. If we wanted to test the null hypothesis that the mean odds ratio is 1.0, the z-value for that test is minus 6.58 with a corresponding p-value of less than 0.001. We see that here, and we also see it here in that the confidence interval excludes 1.0. Next, I'd like to know about the dispersion in effects. Typically, at this point, we would report the q-value, I-squared, and tau-squared. I'm not going to do that. Instead, I'm going to take a few minutes and talk about what we actually have in mind when we ask about heterogeneity. Then, I'm going to show that these statistics do not actually tell us what we want to know. And finally, I'm going to introduce a statistic that does tell us how much the effect size varies across studies. To avoid confusion, let me address a common mistake. A moment ago, I spoke about this line, which reflects the confidence interval. Many researchers believe that this line tells us something about the dispersion in effects. It does not. It tells us how precisely we've estimated the mean effect size. It says nothing about how widely the effect size varies from study to study. This line is sometimes displayed as it is here, and is sometimes displayed as a diamond, as it is in this version of the plot. But in either case, the meaning is the same. The confidence interval is an index of precision, not an index of dispersion. It tells us nothing about how widely the effect size varies across studies. To get a general sense of the heterogeneity, I can sort the studies by effect size as I did a moment ago. However, this plot is not as informative as we might expect for several reasons. In particular, the distribution shown here is the distribution of observed effects, which includes sampling error. What we really care about is the distribution of true effects, and that is what we would see if we could somehow remove the sampling error. To compute the actual amount of dispersion, we do something similar to what we would do in a primary study. We compute the standard deviation of the true effects, and then we compute an interval based on the mean plus or minus 2 standard deviations. If we can assume that the effects are normally distributed in the relevant units, we would expect that the true effect size in 95% of all comparable populations will fall within that interval. I'm going to switch to a plot that actually shows the entire distribution of effects. Unlike the current plot, which shows the effects only for the populations in the analysis, this shows the distribution of effects for the universe of all comparable studies. And unlike the current plot, which shows the distribution of observed effects, this plot is intended to show the distribution of true effects. In other words, this is supposed to show what the distribution of effects would look like if we could somehow remove the sampling error. I've set the scale to go from 0.50 to 1.0. An odds ratio of 1 would indicate that the treatment had no effect. An odds ratio of 0.80 would indicate that the statins reduced the odds of an event by 20%. An odds ratio of 0.60 would indicate that the statins reduced the odds of an event by 40%, and so on. The mean odds ratio is 0.71. I'll plot that here. I can add the confidence interval and a caption. The caption reads, the mean effect size is 0.71, with the 95% confidence interval of 0.64 to 0.79. In other words, we estimated the mean odds ratio as 0.71, but the true mean could fall anywhere from here to here. As I mentioned before, all of this deals with the average effect size. It says nothing about how the effect size in individual studies varies from the mean. Let's look at that now. In a real analysis, I would simply plot the distribution of true effects. However, for the purposes of this video, I'm going to present 3 possible distributions, and then ask which one applies in our analysis. I'm doing this to make it clear what we have in mind when we ask about heterogeneity. Here is one possible distribution. This line shows the distribution of true effects. At one extreme, there are some populations where the effect size is 0.62, and at the other extreme, there are some populations where the effect size is 0.82. The actual numbers are presented in this caption, which reads, the true effect size in 95% of all comparable populations falls in the interval 0.62 to 0.82. This interval, 0.62 to 0.82, is called the prediction interval. If I was asked to predict the impact of treatment in any one population, selected at random from the universe of populations that are comparable to those in the analysis, I would predict that the impact would fall in this interval. And I'd be correct some 95% of the time. In the other 5% of cases, the true effect size would fall to the left of here or to the right of here. So the prediction interval simply gives me the endpoints of this plot. Or does the distribution of effects look like this? At one extreme, there are some populations where the effect size is 0.58, and at the other, there are some populations where the effect size is 0.87. In this case, the prediction interval is 0.58 to 0.87. Or does the distribution of effects look like this? At one extreme, there are some populations where the effect size is 0.55, and at the other extreme, there are some populations where the effect size is 0.92. These are 3 possible examples of what the distribution of effects might look like. Of course, there are an infinite number of other possible distributions. I've picked these 3 to illustrate my point, which is simply that when we ask about heterogeneity, this is what we have in mind. We want to know what the distribution of effects looks like. So, which of these plots corresponds to the actual distribution of effects in this analysis? Because this is so important, I would assume that this information is included in any paper that reports the results of a meta-analysis. As it turns out, however, I would be wrong. There are three statistics that researchers typically report to describe heterogeneity. To see these statistics in CMA, I click Next Table and I scroll to the right. The statistics are presented here. These are the Q value along with its degrees of freedom and a p-value, the I-squared statistic, and tau squared. However, as we will see momentarily, these statistics don't actually tell us how much the effect size varies. The first statistic reported is the Q value, along with its degrees of freedom and the p-value. In this case, the Q value is 13.455, the degrees of freedom is 13, and the p-value is 0.413. On that basis, does the distribution of effects look like this, or like this? The answer is there is no way to know. It could be any of these. The next statistic reported is I-squared. In this case, I-squared is 3.382%. On that basis, does the distribution of effects look like this, or like this? Again, the answer is there is no way to know. It could be any of these. I recognize that this statement will probably come as a surprise, but ask yourself this. I've given you the value of I-squared, which is 3%. Which of these plots actually corresponds to the distribution of true effects? You may or may not guess correctly, but your choice will be a guess because I-squared does not provide that information. Finally, the last statistic typically reported is tau squared, the variance of true effects. In this case, tau squared is 0.001. On that basis, does the distribution of effects look like this, or like this? It actually is possible to determine which of these is correct based on tau squared, but few people know how. So, what statistic does tell us how much the effect size varies? That statistic is called the prediction interval. Here I would report that the true effect size in 95% of all comparable populations falls in the interval of 0.62 to 0.82. And that corresponds to this distribution. Where do I locate the prediction interval? If I'm using CMA version 4, I can simply click this button and the program creates this plot. This caption reflects the information about the distribution. It reads, the true effect size in 95% of all comparable populations falls in the interval 0.62 to 0.82. If you're using an earlier version of CMA, or if you're using another program entirely, you can still create this plot. To do so, you can download a free program on our website. You would simply enter four values as shown here: the mean effect size, the upper limit of the confidence interval, tau squared, and the number of studies. And then click Next to create the plot. At this point, I've explained that the key statistic to address the dispersion in effects is the prediction interval. What about the other statistics? What do the p-value, I-squared, and tau squared tell us? Later in this video, when I explain how to report the results of a meta-analysis, I provide a one-sentence description of each. However, to actually explain what each of these tells us is really a separate lecture. For those of you who are interested, the lecture is available at metaanalysisworkshops.com. And this is also addressed in the text Common Mistakes in Meta-Analysis and How to Avoid Them. The relevant chapter is available for free as a PDF on the book's website. I encourage you to take advantage of these resources. A primary benefit of a meta-analysis is that it enables us to see how the effect size varies across studies. We should always be sure to report this information and to do so in a way that is clear and informative. That is, by reporting the prediction interval. There is one very important caveat to all of this. In order to estimate heterogeneity reliably, we need a minimum number of studies in the analysis. The number of studies needed will vary based on several factors. However, we might use 10 as a useful minimum. When there is variation in effects, and there are less than 10 studies in the analysis, we cannot have confidence that any of the statistics related to heterogeneity will be reliable. This includes I-squared, tau squared, and the prediction interval. Now let's have a look at how we might explain the results. In CMA version 4, I click this button and the program displays this page, which reads as follows. Overview. The analysis is based on 14 studies. The effect size index is the odds ratio. The results of this analysis will be generalized to comparable studies. Therefore, the random effects model was employed for the analysis. Here I would indicate what an effect size on either side of 1 represents, for example, if it favors the treated group or the control group. What is the mean effect size? The mean effect size is 0.710 with a 95% confidence interval of 0.641 to 0.786. The mean effect size in the universe of comparable studies could fall anywhere in this interval. The z-value tests the null hypothesis that the mean effect size is 1.0. The z-value is minus 6.580 with a corresponding p-value of less than 0.001. Using a criterion alpha of 0.05, we reject the null hypothesis and conclude that in the universe of populations comparable to those in the analysis, the mean effect size is not precisely 1.0. How much does the effect size vary across studies? The Q statistic provides a test of the null hypothesis that all studies in the analysis share a common effect size. If all studies share the same true effect size, the expected value of Q would be equal to the degrees of freedom, which is the number of studies minus 1. The Q value is 13.455 with 13 degrees of freedom and a p-value of 0.413. Using a criterion alpha of 0.10, we cannot reject the null hypothesis that the true effect size is the same in all these studies. The I-squared statistic is 3%, which tells us that some 3% of the variance in observed effects reflects variance in true effects rather than sampling error. Tau squared, the variance of true effect sizes, is 0.001 in log units, and tau, the standard deviation of true effect sizes, is 0.038 in log units. If we assume that the true effects are normally distributed in log units, we can estimate that the prediction interval is 0.617 to 0.817. The true effect size in 95% of all comparable populations falls in this interval. Please note that my intention here is not to have the program write the report. I'm simply trying to ensure that statistics are interpreted properly. Next, we might want to create a high-resolution version of the forest plot. I click High Resolution Plot. I click Reset All. I want to set the dimensions of the plot to match the newer version of PowerPoint. If I'm using version 4 of CMA, that will be the default. If I'm using version 3 of CMA, I would click File, Page Size, and Margins. Then I would set the width to 1600 and the height to 900. I'll leave the left and right margins at 50, and I'll change the top and bottom margins to 20. I right-click on the title. I edit the title to Impact of Statins on Cardiovascular Events. I click Font and click the button with one red arrow twice to reduce the font size. I right-click on the plot and click Spacing and Forest Plot Width. There's an area over here called the right buffer. This leaves space on the right side of the forest plot in case I want to add additional columns there. In this case, I don't, and so I want to remove the buffer. I click Right Buffer and Remove. I want to add space between the columns. I click Column Spacing, and then I click the button with one blue arrow 2 times. I want to increase the size of the plot. I click Forest Plot Width, and I click the button with 2 blue arrows. The 2 sides of the plot are labeled Favors A and Favors B. I know that the left should be Favors Statins and the right should be Favors Placebo. I know that because I checked this on the data entry screen. Now I can enter those labels here. I right-click on Favors A. I enter the labels Favors Statins and Favors Placebo. I click Font, and I click the button with one blue arrow 2 times. I'd like to send this to PowerPoint. I click File, Export to PowerPoint. The program opens PowerPoint and inserts the plot. Back in CMA, I can also choose colors for slides and modify any or all of the colors. For example, I could set the colors to look like this, and then send this to PowerPoint again. I can also send it directly to Word. Or I can save this image as a file and then import it into any program. Next, let's generate a high-resolution version of the distribution of true effects. I simply click this button to get the plot. I can edit almost any element on the plot. I'll change the title to Impact of Statins on Cardiovascular Events. Again, I can click File, Export to PowerPoint. That's it for the basic analysis. When we analyze a primary study, we typically perform a sensitivity analysis. This means that we might perform a series of analyses to ensure that the results are robust. For example, we might want to ensure that the results were not overly influenced by one outlier. We can do something similar in a meta-analysis. Here, I'll outline 3 procedures that we might want to include as part of a sensitivity analysis. One issue that we might want to explore is how much of an impact each study has on the analysis. Recall that the summary effect size is a weighted mean of the individual effect sizes. We might want to see how much weight was assigned to each study. If I click this button, I can display a column with the relative weight assigned to each study. Initially, these bars are on a scale of 0 to 100. To see the weights more clearly, I can right-click here, and then I choose Scale Relative to Maximum. This changes the scale so that the differences among weights are easier to see. Additionally, I can sort by relative weight. I right-click on the weights, and I select Sort from High to Low. We can see that one study gets 40% of the weight, and another gets 21% of the weight. We should call attention to this in the discussion. We should also identify the impact of those studies on the basic conclusions. For example, we would want to know how much the effect size would shift if either of these studies were removed from the analysis. To do that, I will rerun the analysis, removing one study at a time. First, I'm going to resort by effect size. To hide the weights, I'm going to deselect this button. At the bottom of the screen, I have a tab for Basic Stats and a tab for One Study Removed. I click on the tab for One Study Removed. Let's focus on WASCOPs, since this is the study that received 40% of the weight in the analysis. Now, the row labeled WASCOPs does not show the result for WASCOPs. Rather, the row for WASCOPs shows the results for an analysis based on all studies except for WASCOPs. On the row labeled WASCOPs, the effect size is 0.692 with a confidence interval of 0.598 to 0.800. This is what we would see on the yellow line if we ran an analysis using the other 13 studies. From a clinical perspective, the result on this line is essentially the same as the result on the yellow line. So the essential conclusions would not change if we removed WASCOPs from the analysis. As I scan the set of analyses, I see that regardless of which study I remove, the basic conclusions remain unchanged. The mean effect size never moves to the left nor to the right by enough to change the clinical implications of the finding. And if we're concerned about a test of the null hypothesis, the p-value is always less than 0.001. So, this plot allows me to report that the results are robust in the sense that the conclusions remain essentially the same with any one study removed. I'll click Basic Stats to return to the standard analysis screen. Next, I'd like to perform an analysis for publication bias. The logic of publication bias is discussed at length in another module. Here, I'll focus on the results. To look at publication bias, I click this button. The program displays what is traditionally known as a funnel plot. The large studies are plotted at the top, and small studies are plotted at the bottom. Most models of publication bias assume that most of the large studies have been published. That's because large studies tend to be statistically significant even when the effect size is relatively small. And even when these studies are not statistically significant, there are various incentives to publish them. Therefore, we expect large studies to be evenly distributed on either side of the mean. By contrast, we expect that only some of the smaller studies have been published. Specifically, small studies that reported large effects would tend to be statistically significant and likely to be published. By contrast, small studies that reported smaller effects might not be statistically significant and might not have been published. For example, We do see a small study with a very large effect here, which pulled the mean to the left. But we don't see small studies with effects in this area. Our concern is that these studies were performed, but were not published because they were not statistically significant. The idea is that if we could somehow recover these studies and add them to the analysis, the mean effect size might shift to the right. I addressed publication bias in another module, and one of the key points I make there is the following. Most of the procedures that we employ to look at publication bias require that we have a reasonable number of large studies and also a reasonable number of small studies. While there is no definitive number for how many studies we need, I think it makes sense to expect at least 5 large studies and 5 small ones. In this analysis, we have only 2 studies toward the bottom of the plot. And if we run an analysis of publication bias, that analysis is not likely to be informative. And therefore, it makes more sense to omit it. That's what I'm going to do over here. For a complete discussion of meta-analysis, consider subscribing to our workshops. These are now available online as well as in person. For information, visit metaanalysisworkshops.com. This is also where you can download the free program to compute prediction intervals. In this analysis, I used the software Comprehensive Meta-Analysis. For information about the software, please visit metaanalysis.com. My name is Michael Borenstein. My email is michael@metaanalysis.com. Please feel free to contact me with any comments or questions.